Hi, I'm hw10q1. Now let's do homework written question 1. This question asks us to collect the definitions and simple properties of the following stochastic processes. The first one is Poisson process. We can define Poisson process xt as follows. When t is 0, xt equal to 0, and xt1 minus xt2 equal to the number of points ti in the interval t from t1 to t2, with the probability that xt1 minus xt2 equal to k equal to e to the power of minus lambda times t1 minus t2, then times lambda times t1 minus t2 to the power of k, then divided by k factorial. A plot like this, we can find that the points in non-overlapping intervals are all independent. The Poisson process method is the probability that xt minus k equals to e to the power of minus lambda times t, then times lambda t to the power of k, then divided by k factorial. Mean is lambda t, and the autocorrelation of Poisson process is lambda squared times t1 times t2, then plus lambda times the mean of t1 and t2. The autocovariance is that lambda times the mean of t1 and t2. We can find the mean of Poisson process is lambda t, shows that the larger time we wait, the expected number of calls is larger. The second one is Poisson increments. We can define it as yt equal to xt plus epsilon, then minus xt divided by epsilon, where xt is a Poisson process. The mass is a probability that yt equal to n divided by epsilon equals to e to the power of negative lambda times epsilon, then times lambda times epsilon to the power n divided by n, where n is the number of calls in the interval from t to t plus epsilon. We can find the mean of Poisson increments is lambda, which is a constant. The autocorrelation is when t1 minus t2 is larger than epsilon, it is lambda squared. Otherwise, it's lambda squared plus lambda divided by epsilon, then minus lambda times t1 t2, and divided by epsilon squared. We can employ it as is. We can find this area equal to lambda. It doesn't depend on epsilon, so when epsilon goes to 0, this area will be at an impulse. The autocovariance is 0, and lambda divided by epsilon, then minus lambda times t1 minus t2, then divided by epsilon squared. third one is Poisson impulse. Zt equal to dxt divided by dt, which is equal to when epsilon is going to goes to 0, yt. As we talked about, when epsilon it goes to 0, this area is still equal to lambda, but it performs as an impulse. So the mean of the Poisson impulse is still lambda. The autocorrelation is when lambda, epsilon goes to 0. The autocorrelation of Poisson increments, which is equals to lambda squared, then plus lambda times delta t1 minus t2. Next one equal to lambda times delta t1 minus t2. We can use zt minus lambda. We can find the mean equal to 0, and the autocorrelation equal to lambda times delta t1 t2, which is a white noise. Next one is semi-random telegraph signal. We can define it as following: xt when k is even in the interval from 0 to t, xt equal to 1, and when k is odd in from 0 to t, xt equals to -1. The math probability that xt equal to 1 equal to e to the power of minus lambda t times cosine h lambda t, and probability that xt equals to -1 equals to e to the power of minus lambda t times sine h lambda t. The mean of semi-random telegraph signal is e to the power of -2 times lambda t. The autocorrelation is T1, T2 equal to e to the power of -2 times lambda T1 minus T2. And autocovariance equal to the autocorrelation minus mean, which is minus going to minus e to the power of -2 times lambda times T1 plus T2. We can find when t goes to infinity, mean goes to 0. When t and t1 and t2 are farther, xt1 and xt2 are less correlated. The fifth is random telegraph signal. We can let a be a random variable independent of xt, with a probability that a equal to 1 equal to the probability that a equals to -1 equals to 1/2, and then we have yt equal to a times xt, where xt is a semi-random telegraph signal. We can get the mass of random telegraph signal is probability that yt equal to 1 equal to yt equal to -1 equal to 1/2. The mean equals to 0, and the autocorrelation equals to e to the power of -2 times lambda times absolute t1 minus t2, and the autocovariance equals to the autocorrelation, because the mean equals to 0. We can find if the probability that yt equals to t1 yt equals to 1 equals to probability that yt equals to -1 equals to 1/2, and the mean equal to a constant, we can get yt is a strict stationary strict stationary. Next one is random walk. We can define it as xnt equal to k times ice, then minus n minus k times ice, which is 2k minus n times ice. The mass probability that xnt equal to r times ice equal to the probability times probability that k equal to n plus r divided by 2, which is this. The mean is also 0, and the autocorrelation equals to autocovariance equals to the mean of the minimum of n and m, and times s squared. We can find when n goes to infinite, we got a Gaussian density. The last one, define the process as a limiting process of random walk, where xt is a random walk, and the s and t and n, s and t goes to 0, and n goes to infinite. Now we got Wiener process. And the probability density function is 1 divided by root 2 times lambda times alpha times t, and times e to the power of negative omega squared divided by 2 alpha t. The mean is 0, and the autocorrelation equals to autocovariance equals to the minimum of t1 and t2, then times alpha. That's it.